Okay, so talking about the structure of hemoglobin, which is one of our globins used to bind oxygen, it does change its conformation when bounded to oxygen. And when it is bounded, we have a change in the interactions between alpha 2 and beta 1, and then alpha 1 and beta 2. So these red curves only. The structure or the interactions between alpha 2, beta 2, and beta 1 and alpha 1 remain the same between states. So it's just the alpha 2 to beta 1 and then alpha 1 to beta 2, as stated here. So as stated before, hemoglobin can exist in two states. You have your T state and your R state. Your T state is your taut or tight state. No oxygen is bound to this hemoglobin, and it is stabilized by ionic interactions between alpha 1 beta 2 and alpha 2 and beta 1, which again are these interactions right here. But those interactions do change when transitioning into the relaxed state, which is the result of O2 binding to the T state, in which again a conformational change is occurring. Again, there's O2 bound to this hemoglobin and it has a higher affinity for O2, hence the binding. So the T state is stabilized by ion pair interactions. So this summarizes the 4 chains in your hemoglobin, and the ion interactions are in dotted lines here that are used to stabilize it. Now, when you get to the relaxed state and hemoglobin is bonded to oxygen, you lose those ion pair interactions just based on how the chain interactions are altered in the conformational change. So you do lose that stabilization. So the transition from a tight to relaxed state of hemoglobin is linked to oxygen binding. So this right here is your heme. And then this is your histidine F8, or your proximal histidine amino acid. And this moves with the binding of O2. So as you can see here, when O2 is bounded, this proximal histidine kind of pulls this heme forward, if that makes sense. And then here is a better image. So in the taut state where there's no oxygen bounded, you have this open gap here in the middle of your heme. And the B1 alpha 2, the beta 1, alpha 2 beta 1 and alpha 1 beta 2 chains are farther apart, so the interaction isn't as great. However, when you do get the binding into the relaxed state of oxygen, it brings the alpha 2 beta 1 and alpha 1 beta 2 chains closer to one another. So that's how it changes its conformation. We talked about how the mutation of the proximal histidine to glycine abolishes cooperativity. We'll talk about what cooperativity is in a second. And it kind of makes this hyperbola curve right here, which indicates that we have lost cooperativity, which is when oxygen binding at one site influences affinity at other sites. So this is heavily implied to be a function of hemoglobin, specifically just because myoglobin only has one site. But then that brings into question the allosteric proteins. So allosteric proteins are multi-subunit proteins that undergo ligand-dependent changes in building affinity. Binding a ligand on one site affects binding to another site, as mentioned before. So we have homotropic and heterotropic. Homotropic is when regular ligand, or O2 in this instance, is used. So an example is hemoglobin. O2 is binding and is changing how O2 binds at another site. Heterotropic is using a different ligand, and this is when binding affinity is altered due to just using a different ligand than O2. So it's not necessarily because O2 is binding, but it's a different ligand that's affecting the other sites. So proteins are dynamic and binding can limit dynamics in other subunits. So I think of like the ligand reducing flexibility at these binding sites. So as you can see, as the ligand gets to these binding sites, the proteins become less flexible and more rigid in structure. So we have a quantitative description of cooperativity using this equation. So we have our protein plus our number of binding sites and number of binding ligands, which equals this function of the protein bounded to the number of ligands available. Our Ka value is just the product of our concentration of proteins and this ligand binding site function over the separate concentrations of the protein and ligand. And this N value changes where it's positioned a bit throughout this equation. So here it's a product with ligand, the number of ligand binding, or amount of ligands that are binding, and it's become a superscript or a subscript here, and then it becomes a superscript in this denominator. And from Ka to your fractional saturation or Y equation, you just have the concentration of ligand with the number of binding sites as the superscript on the numerator and denominator, and the denominator you also are adding your Kd value. So we're talking about the Hill equation in which you're going to have y over 1 minus y equals the ligand raised to the power of binding sites over your Kd value. And what you're going to do is you're just going to take the log of both sides, and that's what this is right here. And this is essentially going to give you your slope for the Hill equation, or the Hill plot, which is right here. And then from here, from this equation to this equation, all you're doing is just rewriting the log as a function. So you bring your power to the front, and then because the log values are being divided, you can subtract the log of each of the numerator minus the denominator. So you can just take n times the log of the ligand concentration minus the log of the Kd value equals log of y over 1 minus y. And so this is your y, this is your m, this is your x, so these two are your slope, and then this is your plus b. So you get your y equals mx plus b. Or, I'm sorry, yeah. And then if you're doing it from myoglobin to hemoglobin, it would just be, you would just change the L to PO2 and then your Kd to P50. So this is the last of the quiz 2 content. So what does the Hill coefficient tell us? So the Hill coefficient, at least according to the textbook, this is not said in class, but this is what I read, it's just n subscript h is a measure of the degree of cooperativity, and the degree of cooperativity is n, in which this tells us the lower limit on the number of interacting binding sites and also the theoretical maximum of the total number of binding sites. So that's when NH equals n. And then again, the n log of the ligand, amount of ligand, is our slope in this instance. So when n equals 1, we have no cooperativity. So that means there's only one active site. An example of this would be myoglobin. Positive cooperativity is when n is greater than 1. So example, hemoglobin, not when it is at low affinity, but elsewhere. And this is like indicating that there's more than one binding site available. And then when n is less than 1, we have negative cooperativity, which is the binding of one ligand impedes the binding of the other. So this is kind of rare. We won't see this one much, but it's good to know. So